Welcome to this explainer. Today, we're opening up our digital notebook to master mathematical sets completely from the ground up. I am so incredibly excited to walk you through this, mostly because sets, well, they're the absolute foundation for logic, probability, and so much advanced math. Today, we're going to look at everything as if we're just sitting down and writing it out together on a clean sheet of paper. We'll solve problems step by step, figure out the actual why behind the rules, and make sure you never get tricked by a set question again. All right, let's dive right in. Here's our game plan for today. We'll start with what a set actually is, how to express them, the different types, subsets, and set operations. Finally, we'll wrap things up with a practice challenge.
Okay, intro to sets. Let's figure out what exactly makes a collection of items a true mathematical set.
So a mathematical set absolutely has to be factual. Opinions literally have no place here. The big key phrase you want to remember is well-defined. The objects inside a set are called its elements, and to be a real, true set, there can be absolutely zero debate about what belongs inside. If two people can disagree on the contents, yeah, it's not a set.
This example perfectly illustrates the difference. Look at the left side of our notebook, the most beautiful flowers. Obviously, this is subjective, right? My favorite flowers might be roses, but yours might be tulips. Because it's based on an opinion, is it a mathematical set? Nope, not at all. But look over at the right side, odd numbers between 2 and 10. That is a rock-solid fact. No matter who you ask anywhere in the world, that gives us the definite, undeniable set of 3, 5, 7, and 9. Watch my digital pen here as we build a set together, step by step, using absolute criteria. Let's use the months of the year, starting with J. First, we identify that this is in fact a factual rule. Nobody can debate the calendar. Next, we draw an open curly brace. That's the universal mathematical sign that we're starting a set. Finally, we just write out the elements, January, June, July, making sure to separate them with commas, and then we close it off with another curly brace. Simple, clean, and perfectly well defined. Moving on to expressing sets. Now that we know what a set is, let's learn the actual mathematical grammar for writing them down.
You'll want to be really careful here and basically memorize these golden rules, especially the fact that you must never ever repeat elements inside your curly braces. We primarily use three methods to show our sets: the listing method, which we literally just saw, the set builder method, which uses mathematical symbols to describe the rule, and Venn diagrams, which are those visual circles. But no matter which method you use, remember that order completely does not matter. The set of 1, 2, 3 is the exact same set as 3, 1, 2. Just think of a set like a bag of marbles. Shaking the bag around doesn't magically change what's inside.
Let's look at a quick trick for translating a word problem into both the listing method and the set builder method, taking it one logical step at a time. So the problem asks for natural numbers greater than 3 and less than 8. Let's call our set y. For the listing method, it's easy. I'm just going to write out the numbers, 4, 5, 6, and 7 inside my braces. But for the set builder method, watch how we write this out. We write y equals, open brace, x colon. That simply translates to the set of all x such that. Then we write x, that little rounded e symbol, which is just math code for belongs to or is an element of, and n for natural numbers. Finally, we add our limits. X is greater than 3, comma, x is less than 8. I know it looks super complex, but really you're just reading an English sentence written in math code. Let's flip to the next page for types of sets, where we classify them by size. Sets generally fall into three main categories. Finite sets have an end. You can actually sit down and count them. Infinite sets? They go on forever, like all even numbers. Then we have the empty set, which literally contains absolutely nothing. We write it using empty braces or a circle with a slash through it, which is called phi. Now, listen closely, because here is a massive trap warning. A ton of students make a mistake here, so let's make sure you don't. Remember that the set containing the number 0 is a finite set with one element. It is not an empty set. 0 is an actual, valid number, so the set has something inside it. Okay, let's do a quick knowledge check. Go ahead and pause this explainer right now and try this one yourself. Ready? Set C is the set of days in a week that start with the letter Z. Well, think about the days of the week. Monday, Tuesday, Wednesday. Do any of them start with Z? No way. Therefore, there are 0 elements that fit this factual criteria. So set C is an empty set. You just write it as C equals phi. All right, section 4, subsets and equality. What's really cool about this part is seeing how sets relate to one another, almost like those Russian nesting dolls. Whenever every single element of a smaller set is also found inside a larger set, we call it a subset. We use a symbol for this that looks kind of like a stretched out letter C. Now, if two sets hold the exact same elements, they are equal. But the absolutely crucial point here is a rule you just have to commit to memory. The empty set is magically a subset of every single set. On top of that, you can calculate the total number of possible subsets any set has by using the formula 2 to the power of n, where n represents the number of elements. Why the number 2? Because every element has exactly two choices. It is either in the subset or it's out of it. Let's actually see this in action. Let's write out all the subsets for set K, which contains the numbers 5 and 9. First off, how many elements are there? 2. So 2 to the power of 2 means we should find exactly 4 subsets. Let's write them all out. First, we list the single items, the set of just 5 and the set of just 9. Next, remember that every set is a subset of itself, so we list the set containing both 5 and 9. Finally, we add our magic rule, the empty set. And look at that. We have 1, 2, 3, 4 subsets. Perfect.
Okay, pay attention because this is a super common exam question, where we use logic to match identical elements across two equal sets to solve for unknown variables, like x and y. The problem tells us the set of 3, 8, and x plus 1 equals the set of 8, 12, and y. Since we know they're equal, their elements must be exactly the same. Let's literally draw a circle around the obvious matches first. Both sets clearly have an 8. Great! Now looking at what's left, the first set has a 3. The only available unknown element in the second set is y, so y must equal 3. Finally, the second set has a 12. That has to match the remaining element in the first set, which is x plus 1. So if x plus 1 equals 12, we just subtract 1, and x equals 11. See how beautifully all that logic just falls right into place?
Section 5. Set operations. It is finally time to combine our sets using mathematical operations, kind of like how we add or multiply numbers.
This overlapping circle diagram, which you probably know as a Venn diagram, is a really brilliant way to visually show how sets share elements. Notice how the middle overlapping section is shaded differently than the rest of the shape. This visual language represents our two main operations, union and intersection. I want you to think of a union, represented by an upward-facing U, as a giant bucket holding everything from both sets. You just dump it all in. But remember the golden rule, no repeating elements. An intersection, on the other hand, represented by a downward-facing U, is like a strict VIP list. An item is only allowed on the intersection list if it belongs to both set A and set B. Watch closely as we handwrite the solution to an operations problem together. We have set A with 2, 4, 6, and set B with 4, 6, 8, 10. Let's do the intersection first. Look at the two lists. What numbers are in both? Well, I see a 4 in set A and a 4 in set B. Let's write that down. I also see a 6 in set A and a 6 in set B. So our intersection is simply the set containing 4 and 6. Now for the union. I'll just write down all of set A to start, 2, 4, 6. Now I'll look over at set B to add the rest. B has 4 and 6, but we already wrote those down and we never repeat. So we just add the 8 and the 10, meaning our final union is 2, 4, 6, 8, 10.
Let's look at a slightly more complex scenario with 3 intersecting circles. Here we have sets P, Q, and R. The real beauty of the Venn diagram is that all the elements are already perfectly organized for us. Everything inside the P circle belongs to P. Everything in the Q circle belongs to Q, and those overlapping shapes show us the intersections visually without having to mentally scan through long lists of numbers. Which actually brings us perfectly to our final test.
The practice challenge. Let's see if you can apply all these notebook rules to one final, real-world classwork problem.
Based on everything we've just covered, pause this explainer one last time. Looking at the diagram or the written sets, can you find the exact intersection of P and Q? Okay, let's look at where circle P and circle Q overlap in the diagram. There is a single number sitting right inside that shared football-shaped overlap. Alternatively, you can just look at the written sets. P has 8, 4, 5, and Q has 2, 5, 9. The only number on both VIP lists is 5, so the intersection is the set containing the number 5. Fantastic, we have totally mastered the rules of finite sets today, but before you go, think about this. What happens if we apply these exact same rules to infinite sets? If a set literally goes on forever, can one infinity actually be larger than another infinity? I'll leave you to ponder that mind-bending question. See you in the next explainer.